Hello, everybody. Welcome back to Math 100. Today, we are to cover the last section of chapter 4. So this is section 4.4, and it's about expected value, and what is known as the law of averages, sometimes referred to as the law of large numbers. It includes the gambler's fallacy, which is a fallacy that is believed by people who gamble, people who take risks, which, by the way, is all of us. We talk about risks and expected values and how those ideas influence pretty much every decision we make. Okay, so let's start. We will do section 4.4. Section 4.4 is titled The Law of Averages and Expected Value. All right, so we'll talk about expected value. That is something we can calculate. And then the law of averages is actually just a empirical observation on what happens with probabilities, risks, and expected value. All right, so what is the main question here is what is expected value and what role does it play in every decision making as we live each day of our life, right? And so we start with what is closely associated with the idea of expected value. And that is the law of averages, sometimes called the law of large numbers. Right, and this is an important step in considering expected value. What can we expect, right? So maybe I should say something about the risks here. You know, we take risks every day, whether we like it or not. It's all about risks, right? And we'll talk about this, the everyday ramifications of decision making and expected values at the end of this lesson. Right, but when an independent, so here's the law of averages. When an independent trial, I'll explain what that means, is repeated many times. Okay, so you do the same thing over and over again, and that is what the large numbers is referring to. Then the actual probability of some event approaches its theoretical probability. So what actually happens is going to get closer and closer to what we calculate. Right? I should also say this theoretical probability is what I mean by mathematical probability, which we can compute. Probability. All right. So for instance, how likely is it to get, all right, so let's say, you flip your coin, all right? What is the probability of getting tails on the flip of a coin? 1/2. How about of heads? 1/2, okay, no problem there. So it's nothing unusual if you flip a coin once and get heads, okay? If you flip 2 coins and if you get 2 heads, is that unusual? 2 heads out of 2 flips. Well, I mean, it's sure, I mean, that happens, right? I mean, it's like having 2 kids. What's the probability? Is that unlikely that you have 2 boys? Or is that unlikely that you have 2 girls? Why not have a boy and a girl or girl and a boy? Well, sometimes it happens, right? And it happens many times that out of the 2 children, you'll have 2 boys or something. So having 2 heads out of 2 coin flips is not unusual. But if you have 10 heads, when you flip the coin 10 times, there is something unusual, right? That really shouldn't happen. You shouldn't have heads all 10 times when you flip the coin 10 times. And so that is what we mean by the law of large numbers. Now, let me ask you this question. If you are to flip a coin 10 times, okay, 10 times, or if you flip 10 coins together, okay, it doesn't matter. You are sort of expecting to get about half of them to be heads and half of them to be tails, right? But how likely is it to get 7 heads out of 10 coin flips? You don't always get 5, right? But you will often get 7 heads out of 10 coin flips. That's not all that unusual, right? So you can say this is not very likely. You don't expect to have 7 or more heads when you flip 10 coins or flip a coin 10 times. So this is not likely, but it's not really unusual. Not very unusual either. Okay, so 7 out of 10 is not so bad. I mean, it just happens, right? What happens if you have 14 heads out of 20 coin flips? Okay, now that's somewhat unusual, because you would expect, as you practice, as you try, and as your sample space gets bigger and bigger, you would expect that number to be about half of this number. Yeah, that's exactly what the law of averages says. All right, so if you have 700 heads out of 10,000, out of 1,000, 700 heads, so 70% heads out of 1,000 coin flips. Now it turns out this is highly, highly unlikely. In fact, it's very unlikely. You can calculate the probability of this happening. What is the probability of getting 700 or more heads? In other words, 70% or more when you flip 100 coins, or when you flip a coin 100 times. And it is very, very unlikely. Okay, and so the law of large numbers basically says that as the number of trials, in this case the coin flips, as that independent trial is repeated over and over many times, a large number of times, then what really happens is going to approach its theoretical probability, which is the mathematical probability. Okay, all right, so that's the law of large numbers. Now, suppose here that you have your favorite NBA player, okay? And your favorite basketball player has an 89% average on free throws. That's fairly good, right? As we saw, typically you would expect like 83%, even from players like, LeBron James or Kobe Bryant. How likely is it for him to miss 2 out of 3 free throws? Okay, is it possible, like in one game, that your favorite player who has an average of 89% success rate on free throws, is it possible for him to miss 2 out of 3 free throws? Yeah, that's not so unusual. Maybe he's just having a bad day. So missing 2 out of 3 could happen in a bad game. Maybe unusual, but not so unusual. Right? Okay. Missing 20 out of 30, however, is in a month. Okay, that's weird, right? You wouldn't expect that to happen from a good player. So at this point, you may wonder something else may be happening. So missing 20 out of 30 is different from missing 2 out of 3, although the percentage is the same. So missing 20 out of 30 would be highly, highly unlikely. Maybe a rumor of an injury could start, right? So, but how can we say that? Because that's either way, it's 2 out of 3, 20 out of 30. That's like, that's just like the same percentage. But the point is, the more you repeat this process, the larger number of times the trial happens. Okay, you would expect this the successful number to approach 89%, right? Not missing 66% of the time. All right, that leads to what is known as the gambler's fallacy. And there are a couple of fallacies here. All right, so I want you to think about this. This is not something that you should just study for your exam. This is, this is really probably will start changing the way you think about risk and the future and everything. All right. Suppose you notice that in a certain roulette table, okay, at least 6, so the last 6 spins, you have been watching this like last 6 times. The last 6 spins all resulted in an odd number. You say, that's interesting. We have an odd number and we have another odd number. And so the odd numbers happened 6 times in a row. Now you're ready to make a bet. Which one of your friends below is right? Your friend A says, hey, look, bet on even. And you say, really? Because for the last 6 times we got an odd number. And your friend A says, exactly, it's overdue. We are supposed to get an even number. Right? You can't always have odd numbers all the time. So therefore, you should bet even, because eventually things could balance out. And another friend of yours, B, says, you know what, you should bet on odd. That's obvious, right? Because look, we have a lucky streak happening here. 6 spins, the last 6 spins have been odds, so you should bet on an odd number. And friend C says, it doesn't matter, your chances are the same either way. So which of your friends is right? All right, let's think about this. Can you figure out which one's right, if any of them is right? Right, so here's the answer. A and B are called gambler's fallacy examples. Right. So A is basically saying, look, things need to balance out. It's overdue. So the next one will be more likely to be even. Okay. Well, that doesn't happen. Okay. Because why is it? Well, it turns out the probability, if this roulette is the standard one, and if it's fair and there is no trick involved in this, the probability of getting an odd next is exactly 1/2, regardless of what happened in the last 6 spins, or last 1,000 spins for that matter. Okay, so A and B are gambler's fallacies. A is wrong because A seems to indicate that even has a better chance because it's overdue. B is also a fallacy because there is no such thing as a lucky streak if you assume that the roulette is a fair one. Right. So C is correct. The probability of getting an odd next is exactly 1/2. And by the way, this is really not all that important, but there's a little difference between an American roulette and the European roulette. In American roulette, you have 38 divisions. You have numbers 1 through 36, and then there is a 0, and there is a 0, 0. Okay, so some of you may be more familiar with this than I, since I don't gamble. The probability of getting an odd number is 18 because there are 36 numbers, 18. But remember, in a total there are 38 slots, so the probability of getting an odd number is 18 over 38. And the same thing, the probability of getting an even number is 18 over 38. They don't add up to 100% because of these two slots named 0 and 0, 0. Okay, so it's not like you always get an even or odd, but the probability of getting an even next will be precisely equal to the probability of getting an odd. Even and odd would be exactly the same here. Right? But you will hear people talk like this friend A or friend B. So be very careful, and just be aware when people say things like what A and B are saying. Okay. Your friend D, another friend comes in and says, don't gamble. This may be the best advice. I hate to say this, all right, but whenever a casino is set up, the probability, and they calculate what is known as the expected value, which we will study in the next page. They calculate it so that the house always has an advantage, and not surprising, right? Because it's a business. They have to make money in order to survive in their casino world. And so you, as the best advice for you is not to gamble. Okay, the old saying, what's the best way to make money? And only way to make money at the casino is to own the casino. And so that is, I think, very sound advice. Okay, let's go to the second page. And this is about the expected value. Most of your questions on your homework and the quiz and the test will be on this idea of expected value. I'm going to do the first one, and then I will stop and then go to the second part of this video where you would continue. But I want you to see how to do this first one so you can attempt to do your second one on your own before you start on part B. Sounds good? Okay, so let's say the expected value, maybe I should say this first. The expected value is the average value of win or loss of playing one game. Now you can play hundreds of games, or the game, you can play the same game 100 times. But the question is, on the average, sometimes you win, sometimes you lose, but on the average, how much would you expect to win per game? And that value is called the expected value. When prizes and probabilities are given, you can calculate the expected value of a game. All right. So here's the first example. Let's say you roll a die. Okay, and it doesn't cost anything to play this game. You roll a die, okay, and if you win, no, sorry, if the outcome is a 1, if you roll a die and if a 1 comes up, then you get $6. Otherwise, you lose $2. Okay, would you play this game with your friend? In other words, you get $6 every time you get a 1, and otherwise you lose $2. $6 is a lot of money, right? So maybe it's a good game to play. The question here is, how much would you expect to win every time you play this game, right? And game in this case is a roll of a die. If you do this 100 times, that would be considered 100 games. So what is the expected value of this game? And you can, and by the way, there are 2 ways of doing this kind of a expected value problem. There is a concept of, let me write this down. There's a concept of, yeah, let me go ahead. 2 methods. One method is called a weighted sum. Okay, and so there's a formula that I could give you. I'm not going to do that. In fact, if you're interested, you can find the weighted sum formula in the book. But there is a way to calculate the sum of the products of the probability and the value of that event happening. And that weighted sum is going to give you the expected value. I am going to give you a more intuitive approach, which is play 100 games or 1,000 games, etc. Okay, and find the average value. This is very much like that hypothetical 1,000 the chart. Okay, when we talked about false positives and so on, because this is by far the better and the most intuitive approach. It does not depend on the formula, but it'll make you think. And because you're thinking, it's easier to make sense of this method. All right, so here's the way to think about this one. Okay, maybe I can draw a little chart and explain this. All right, sometimes you win $6, sometimes you lose $2, right? Let's play this game, I'm gonna say 600 times. Now, why 600? Because this time, you know that the probability of getting a 1 is 1/6, right? And probability of getting something besides 1, 2, 3, 4, 5, or 6 is 5/6 probability. All right, so if you play this 600 times, you are going to win 1/6 of the times. 1/6 of 600 is 100 times. So if you play this game 600 times, you are expected to win 100 times. Each time you are going to get $6. So the gains, the winnings after you play 600 games is expected to be 6 times 100. That's $600. Great, you are going to win $600 if you play this game 600 times. But remember, you lose the rest of the times, 500 times you lose. Okay, so remember, we are fictitiously, theoretically only playing this 600 times. You win 100 times. Each time you win $6, that would be the net. That would be the gain of $600. You lose 500 times, and each time you lose $2, and therefore your loss would be 2 times 500, and that's $1,000. Let's put negative. Well, it's you lose $1,000, right? So you can see the net gain is going to be negative 400. Okay, so in other words, if you play this game 600 times, you expect to win 600 but lose 1,000. So altogether, your net gain is negative 400. So you divide this negative 400 by the number of times you play. That's 600, and that turns out to be negative 2/3. Okay. So your expected value is exactly this. This is the number of dollars, so that's negative negative 0.666, and so that's 66. Let's say round to the nearest cents, negative 67 cents. Okay, does it make sense? This number is representing how much you are expected to win each time you play this game, and the answer is every time you play this game, you expect to lose 67 cents. And in fact, if you play it 600 times, be ready to lose $400. That's what the expected value is. All right, with that in mind, try to do this problem and maybe this one. And once you are done with these, go ahead and click on your second part of the video, and I will conclude this section at that time. But try these first, okay? That's good for you.